I'm going to do compute this integral, and I'm going to start by drawing a sketch. I'll draw a somewhat big one over here. That's a nice straight line. That one isn't so good. And I'm going to draw the circle, and I'll draw it in green. Here it is, and this has radius 2. And so the first question I always ask myself is, especially with a curve that's nice like this, and maybe I should give the orientation too. Right. So this is counterclockwise. This is contractible to the point 0. So if the integrand is holomorphic, that means the integral is going to be 0 and I'm going to be done. Because circles are ridiculously nice. But it's not. This actually has 2 points where it's not holomorphic, and that's at 0 and at 1. I have problems at those 2 points. Now, since the integrand is not holomorphic, my next step is to say, can I use Cauchy's integral formula? Cauchy's integral formula says that if you have, again, a nice enough curve, the integral is just going to equal to 2 pi I times f of w. And there are also variations of it, right? F of z minus w squared equals 2 pi I times f prime of w. That's a prime. So these are the 2 formulas I want to use. And notice they both almost work, except they need to exactly work. So I need to figure out how to incorporate these formulas, but neither of these formulas work here. So I'm going to use a trick. It's probably the most popular trick in mathematics. I'm going to say that this thing is equal to itself. You might see what's coming here. Plus 0. Okay, but I'm going to write 0 in a kind of a unique way. And that is, I'm going to draw a line right down there in this direction. So, and I'll call this curve gamma. And so then what I can say is that this is equal to the integral dz over z squared times z minus 1, z equals 2, plus the integral of gamma dz z squared z minus 2, plus the integral of negative gamma, so they cancel themselves out. Okay, so what I have here, and I'll do this in a dark, let's do something really different. How about do it in orange? So I'm also taking minus gamma. The blue and the orange should actually overlap, but I'm drawing them separately so you can see them. So the orange should be right on top of the blue, and they just cancel each other out. So what am I doing? I'm integrating, and essentially what I'm doing is at every point along this green circle, I'm adding up the value of the function. But I'm also going to add up the value along here and the value along here. Now the order in which I add them up actually doesn't matter, as long as I follow the orientation of the curve. So instead, what I'm going to do is I'm going to split this into 2 integrals, which maybe I'll call I'll call this alpha. And that is just this part right here, just kind of the right part of the circle. And then I also have another part, it's purple. Oops, sorry. Like this. This is the curve beta. So I can split this into a right half which I'll call alpha, and a left half which I'll call beta, and then I can just compute these. So equals the integral over alpha plus the integral over beta, which I can write, alpha only has one bad point inside of it, and that's 1. So I can rewrite this as 1 over z squared over z minus 1, like so, dz, plus the integral over beta, which is 1 over z minus 1 over z squared, because the only bad point is that. Now I can just use Cauchy integral formulas. 2 pi I times, I'm just going to wrap this up, and one more screencast is going to take like 10 seconds. Wait 1 second.